Question?
Hey, Aksharish.
Hey.
Hey, Bobby.
Yeah. Is the connection good?
Yeah, it seems like it.
We don't have an exam on Monday, right? We have homework due on Monday.
Yeah.
Oh, okay. So I can go slow. While I was thinking about it a few minutes back, I was thinking there's an exam on Monday. I was going to have to finish things today. Yes. Okay. So we have homework 9 due on Monday, October 19. And midterm 3 seems like very fun. Any questions in general? So now we are only 3 students. I think, yeah, Travis attends. He regularly attends online, and Riley and Matt sometimes show up. Yeah, okay. So we talked about fields generated, or electric potential and electric fields generated by permanent polarizations, especially for a slab. And now we want to do a spherical permanent, so a sphere. The sphere, is this visible? No.
I'll just have to
Just zoom out a little, right? Ah, where? Too far. Ah. I think
should be good.
you could write if I don't write.
Running higher.
Yeah, I cannot reach that. Sphere with permanent polarization. Okay. So just a spherical material. That's your sphere. Let's say its radius is what should I say? R. Capital R. Is it right? Yeah, capital R maybe. And we want to have a permanent polarization to it. Let's choose this to be in the z direction. So remember, polarization has to do with, so polarization by definition is dipole moment at a microscopic level per unit volume. We talk about charge density as charge per unit volume. Now we're talking about how much dipoles are there per unit volume. So these are all tiny, tiny dipoles. They're all lined up in the z direction. Right? That's the way you want to imagine it. Typically, for example, if it is a magnet, there are two possibilities. Either it is already lined up, or if you apply an electric or magnetic field, they line up. So this is a permanent polarization, so this is already lined up material. Right, so it's kind of a dipole should always be imagined like a magnet. So the electric field will be those of a magnet, so which is a dipole. Right, but we want to see how it comes about. So polarization, we say, is P, a vector. A vector has R dependence, but we are saying that it is mostly uniform, except that at the boundary that should stop acting, right? There should be no polarization beyond the boundary of the radius of the sphere. Right? So this is Z hat, right? That's the direction inside the sphere. Actually, let's not keep it Z hat, because why should we keep it in the Z? We can rotate this also, right? So let's say this is some direction P naught, some constant vector P naught, and then we have to pick the fact that it is only inside the sphere. So this is R, the radius of the sphere should always be greater than the radius of the source or wherever you're observing, if you want. So if this is a source, so then maybe we can also say this is R prime, then this is R prime. So as far as R prime is less than capital R, then it contributes, otherwise it's 0. Right? So that's the way it is. So this should be clear, right? Our step function is equal to 1 if x is greater than 0, and is 0 if x is less than 0. So if I were to flip this, so if I put minus x, that's equal to 0 if, so this becomes the opposite, right? And this is 1 if it is greater than 0. Right, that's your understanding, and if you apply it here, that means radius greater than, radius should be greater than the source. Okay, so that's good, but we said this, whenever you have a polarization, the effective charge density, so there is an effective charge density. There is no charges as such, but there seems to be an effective charge density, and that's equal to negative of the divergence of your polarization. So if we take the divergence of this quantity, that's what that is the charge contribution. That is how this whole material behaves. So that's the same as minus of the divergence of, put this whole thing inside, so it's step function R minus R prime. This is magnitude, that's not a vector. Right? That's how you would act on it. This is a constant vector, so the gradient doesn't act on this. And so the gradient only acts on this piece. So what we have is, so instead of doing that, I'll flip these two because this is not going to act on that. So why worry about that? This is the same as E naught divided with gradient acting on or prime. Right, that's the same thing. Again, in principle, it should act on this and this should act on that. But since this is a constant, that doesn't contribute. And when it acts on this, since it is dotted with the vector, it can be written in that form. But now we have gradient of the step function. That's basically a delta function. But we know that this acts only in the radial direction. So let's see that more carefully. So the gradient acting on the step function, or minus or, so that's no vector, so that's scalar. And I should actually be a little careful since I said this is R prime. Right? I'm pretending all these are sources. So this gradient here should be primed. So this is the derivative with the primed variable. And the same thing here, and the same thing here. That means to say that this is d by dr prime. Right? There's a r, there's a source, and a, let me say, the observation point will be, this is the observer, which we have not introduced yet, and r prime is your source. So this is your prime, and that's equal to, if we go to spherical coordinates, this is r hat times d by dr times plus theta hat plus 1 over r d by d theta. That's the gradient, that's how the gradient looks like. So I should actually again make it primed, 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 plus phi hat prime and 1 over r prime sine theta prime d by d phi prime. That's a whole operator for the gradient and in spherical coordinates, and this whole thing acts on okay. But this does not depend on the angles. So this operator doesn't contribute. This operator doesn't contribute. Right? The operator is completely in the radial direction. And that's equal to r prime d by d r prime times but the derivative of a Heaviside step function is nothing but the delta function, but since this is coming with a negative sign, there's also a negative sign. So negative r prime, and that's a delta function. And it doesn't matter what's delta function, doesn't look at the sign, right? It is r minus r prime minus r. And the negative sign comes because the derivative of the argument, and then inside the argument there is this negative sign in there. Okay, so that's your charge, effective charge density. That negative sign contributes here. So this is P naught dotted with r prime, r hat prime, and that is a delta function. Oh, I actually wrote it wrong. I think these are not vectors, right? So this is not a vector. That's not a vector. Yeah, I was not being careful. These are magnitudes, so we shouldn't be. What this means is that this whole material, when it comes to generating charges, this behaves as if there is a positive charge on this. This is equivalent to, this is a material with dipole moment uniformly spread out. So this is equivalent. This is equivalent to a sphere which has charge density distributed on it, but only on the surface. This is equivalent. Remember that these are all negative, positive, but then this has a, since this is r hat, this has a cosine angular dependence. So this means that there are more charges on the north and south pole than there are. So here there is 0 actually. There is less charge here, less charge here, less charge, and almost 0 on that. In fact, this distribution is cosine theta prime. P naught dotted. Nice.
Oh, sorry.
Good. So he or she didn't like dipole moments. Maybe it was also trying to study ENM. Okay. So, so this is, if this was in the z direction, so this has a cosine theta dependence, right? So this is P naught cosine theta prime. Or let me not say cosine theta prime because I'm going to use this later. So this is the angle, right? Cosine of the angle between P naught and R prime, right? But whatever that angle is, that contributes 1 here and 0 when it is perpendicular to that. So this is like a dipole field here. So again, the whole material with a dipole moment density behaves for all electrical purposes as if the charges, there was a sphere with charge distributed on the surface alone, nothing inside. This is a delta function on the surface, as if this distribution is like a cosine distribution. It's not a vector, notice, this is a scalar. So if that is the case, we can actually calculate the electric potential. Because that's a delta function, probably it's easier to evaluate. So let's evaluate the electric potential due to, this is the observation point now, or due to this effective charge density is equal to 1 over 4 pi epsilon naught d cube r prime times, usually it is charge density, but now we say it is effective charge density. Effective charge density has to do with the charge density associated with the polarization. So that's a negative gradient of T that shows up. That's over R minus R prime. Do that explicitly. Right, so that's equal to 1 over 4 pi epsilon naught yeah, a few more steps. So this is d cube r prime. That's P naught dotted with half prime divided by R minus R prime. So we square this, so R squared plus R prime squared minus 2 R dotted with R prime. That's what it is. Notice that there are 3 vectors in action here. So let me show that explicitly. That's your let's say in general, I have my R here. That's my observation point. It could be outside, inside. There's a small r prime here, which is usually inside the sphere. Sphere somewhere here. And there is also the polarization P naught. Right? So that's your 3 vectors. And in general, these 3 are different vectors. We do know that R prime we want to integrate over this whole sphere. In fact, it will only be on the surface of the sphere. P naught is a fixed vector, and observation point is wherever you choose to observe. Let's choose our, so we have our, we can choose our axis at once we can actually rotate it. And let's choose at this point. So let's choose, right? So this is just for simplicity. Choose R along Z, or your Z hat to be along R. So you choose your Z axis to be along the R hat. And that's necessary because that actually makes this denominator simple. Necessary in the sense if you want to use elementary integrals, but if we use legendary polynomials, actually we can do this even without invoking all these choices. But let's say we are choosing this along the Z axis. So let's write down what these vectors are. So our R prime is equal to, this is I hat sine theta prime cosine phi prime plus j hat sine theta prime sine of phi prime plus k hat cosine theta. We said R is along the Z axis. So this is R prime. So this is Z I hat 0 plus j hat 0 plus k hat along. So let's just say that's R, right? R is basically Z then in that case. And this is theta prime. And we also have P naught. And we can say this is I hat times P0x plus j hat times P0y plus k hat times P0 z. We won't use this form in general, but this is the understanding. Then, what is vector R over vector R prime? That's one of the constructions that's showing up, and that is P naught over R prime. R over R prime is simply R cosine theta prime, or R prime cosine theta prime, because this is a unit vector. So that's a simplification that otherwise, if we don't choose the z-axis here, this will be actually a complicated expression. So our integral is phi of r is equal to 1 over 4 pi epsilon naught times integral. There are three integrals in R prime. That is 0 to infinity R prime square R prime. There is 0 to pi sine theta prime d theta prime, and there is 0 to 2 pi d phi prime. Great. So that's here d cube R prime written completely explicitly. And I also have P naught dotted with R prime. So I'm going to write that as, I'll write P naught as it is. And R prime, I will write this quantity in. I hat sine theta prime cosine phi prime plus j hat okay. Seems very messy, but many things will collapse very quickly. That's divided by and collapse very quickly if we use Legendre. So it's R squared plus R prime squared minus 2 R prime cosine theta prime. And did I miss something? What did I miss? So I had noticed that here I was supposed to write the charge density here, effective charge density. I said that's a delta function, so I should have copied the delta function there, right? So this is the delta function is also there. So basically it is setting all the r prime to r prime. So it will allow me to do that integral right there, and that shows up here, and there is a delta function sitting there. I have room to put that in. That should be in. First thing to notice is that this has no azimuth dependence, azimuth in the sense phi prime dependence in here. This whole integral, as far as the denominator goes, the potential doesn't have any phi prime dependence. So only phi prime dependence is here and here, the sine phi prime and the sine phi prime. So I can take this integral in all the way there. And what is the integral of 0 to 2 pi of cosine phi prime? So integral of 0 to 2 pi d phi prime cosine of phi prime will be how much?
Just 0.
It's 0, right? Very good, because it's a periodic function, 0 to 2 pi. So upper half plane and 0, this cancels out, right? So that's, or you can say this is sine of phi evaluated at 0 and 2 pi.
Yeah.
So that's equal to 0. Very good, right? And the same thing with 0 to 2 pi d phi prime sine of phi prime. This is cosine of phi prime, 0 to 2 pi, one is 1, the other one is also 1, so 1 minus 1 is 0, right? So that's equal to 0. Or you can think of this as periodic functions, right? So this is a cosine phi plot. This area will exactly cancel that area under those plots of 0. So that means that this piece here will be 0. Like this integral is actually 0. So this doesn't contribute. Sine of phi also doesn't contribute. Right, so the only thing that contributes is the z hat direction, that is p naught dotted with k hat, and that's the contribution that comes in. So if I were to go to the other board with this, that's equal to phi within. Yes. Is that visible on the other side?
Yeah,
Yeah.
that's okay.
Oh, okay. So this is phi of r is equal to 1 over 4 pi epsilon naught. Since there is a delta function, I immediately evaluate that. Just I have to remember to replace everywhere I see r prime, I have to replace it with capital R, right? That's how you operate the delta function. So wherever I see r prime, anywhere, I have to replace it with capital R. So this is the first place I see. That's r prime, that's r squared. And forget that, drop the r prime integral because that's delta function. This stays. So that stays 0 to pi sine theta prime d theta prime. Then there is p naught dotted with k hat. Oh, that is also the phi prime integral, right? So it's phi prime integral 0 to 2 pi d phi prime. And the only piece that survives is p naught dotted with k hat, and that's cosine of theta prime divided by r squared. R prime gets replaced with capital R. So it's minus 2 or capital R cosine of theta prime. There is no phi prime dependence here anymore, so that's 2 pi. That whole thing is equal to 2 pi. That integral can be done. So bring it outside. So that's 2 pi r squared divided by 4 pi epsilon naught. And the p naught dotted with k hat doesn't have any angular dependence. That also comes out. And I have an integral which is 0 pi sine theta prime d theta prime and cosine of theta prime or square plus this whole quantity, let's call this an integral I. So this is equal to, we will do that later. Let's say we did a very similar integral when this cosine theta was not there in the numerator. That gave us legendary polynomial of the 0th order. This is actually the legendary polynomial of the 1st order, but we'll do that on Monday. But as of now, let's just say this integral is equal to that is a 1 over length as our dimension. So this is 1 over r, capital R over r, right? So it is basically r over r squared. Let's note that as, since I'm not doing this. If r was less than r. That means to say if the observation point is outside the sphere, that's your answer. And that is a factor of 2 by 3. Sorry. And it is.
Is this the answer for the right part of the equation?
Yes, only this.
Okay.
And I'm going to write this already. So this is equal to, yeah. So let's say this alone is equal to. And this is 2 by 3 small r over r squared if r was inside the sphere. So this is inside of the sphere. This is outside the sphere. Last time we talked about inside the slab and outside the slab. This is the same scenario. So that's simple. So I'll cancel this out. So there is a 1 over 2 epsilon. Right, and actually there is 1 over 2 there and a 2 coming from there also. So there is 1 over 3. Let me write it. So 2 pi, 4 pi, 1 over 3 epsilon naught. Okay, so 2 pi r squared over 4 pi epsilon naught and E naught dotted with k hat, and that is 2 by 3 r over r squared on one side, and the other one is 2 pi r squared 4 pi epsilon naught. With this integral, which we'll do somewhere else. This is 2 by 3 r over capital R squared. And this is inside. Notice when you're inside, the capital R squared cancels out. And when you're actually outside, this pretty much gives you the volume, right? R cubed is the volume of that sphere that is showing up. So let's say, so let's write this. Yes, Christian?
No.
So this can be written as, So when it is outside, it is 1 over 4 pi epsilon naught. Let me provide an R in here and divide by R. And remember, we chose our z hat to be in the direction of observer, right? This was our observer. So now that we have reached here, let's upgrade it to a more general scenario. And this is release the fact that we chose that to be in that direction. So this can be now an arbitrary R hat direction. And that's R hat becomes vector R over small r. So with that feature, what we have is 4 pi by 3 r cubed. That's your volume of the sphere times p naught dotted with r over r cubed. This might be a familiar expression. Do you guys recognize this by any chance? From what we did before in the last 2-3 weeks? This piece alone here? Sort of. Anyone else recognizes? This is the dipole, right? Electric potential due to a dipole looks exactly like this. Like if it was 1 over r, it is a charge, and if it's a dipole, this looks like this. So it seems like this is a dipole times a volume. Right? So that's what the field is. So this is like a dipole contribution. That is when that is outside. Let me write outside. That's outside. But what about inside? Inside it seems like there is a vector r. So again, if I do the same thing, so 2 this time cancels. So this is just 1 over 3. So 1 over epsilon naught, right? And then there is p, let's say 1 over 3, 1 over 3. And this is p naught dotted with vector r. This was r hat, but then multiply by, so z hat gets upgraded to r hat, z hat is k hat, right? K hat gets upgraded to z, r hat, which is nothing but vector r, nothing in the denominator because r's cancelled out, and that's how I'll illustrate. So that's what it is inside. Did I lose correct? Yeah, that's correct. So that's all electric potential, right? So we should remember that this is all electric potential, but now we can do the electric field. Electric field, we just take the gradient. Right? So this is negative electric field would be equal to negative gradient of the electric potential. So let me use this as volume V. V times P naught. So that's just a slight simplification in that. So that's equal to because remember, P naught is dipole moment per unit volume. So that's per unit volume and the volume cancels out. It gives you the dipole moment structure. So this is the same as, so this will be equal to 1 over 4 pi. So there's a negative 1 over 4 pi epsilon naught. And actually, let's define the total dipole moment to be 4 pi by 3 r cubed, the volume, multiplied by the microscopic polarization, right? P naught. So that's a dipole moment of that whole material, volume multiplied by the dipole moment density. So that's the same as gradient of E with R cubed. Actually, this is also good to realize that a magnet, like when you think of a simple magnet, a north pole and a south pole, its field is given by this. Like it's a dipole field, although like when you think of a magnet, north pole, south pole, it has this fields, right? Its equation is this. That's your electric potential, and if you take the gradient of that, that's the equation for that. Typically, we don't see that in early courses because of the complications of the vector nature of that. This is outside. And we know that that's a dipole field, so I won't even expand this out. We can actually expand it, so it's a dipole field. But we are more interested in the inside. Right? Outside is dipole field. Inside is negative gradient. That is 1 over 3 epsilon naught. And gradient of vector R dotted with P naught. But remember that gradient and a position vector, that's just your unit dyadic. So that's simply 1, and 1 unit dyadic multiplied by P naught is simply P naught itself. So that's equal to, this is a dipole field. So let me just write dipole field outside. And inside is minus 1 over 3 epsilon naught times P naught, the vector P naught. This is outside, and that's inside. If I were to do this plot, so you have the sphere here. Can they see this? Yeah. So that's your sphere. Outside is a dipole field. Right? So this is the sphere, that's your dipole field. That's your dipole field. But inside, notice the negative sign, polarization is in the up direction. Let's say if we pick that to be in a particular, in the vertical direction, this is 1/3 of that in the bottom direction. So that's your electric field lines. This is electric field lines. So that's your field lines, electric field, so E. Right, that's your electric field line. Inside the material, it is pointing downwards when the polarization actually is in the upward direction. But we said that displacement vector D is equal to epsilon E, the electric field itself, plus the polarization of the material. And if I were to add this, like we saw last time, they sort of inside the material, they come in opposite direction. Outside is the same because P naught is 0, stays the same. This is dipole still, dipole field. But inside is, you have to add this to this quantity. So minus 1/3 plus 1. So that's plus. So this changes sign now. And this is plus 2/3 times P naught. So if you were to now plot D now, the displacement of the constitutive field, right? That's your D. Again, plot my D. This is the dipole field again. No change. But now the displacement gets a contribution from the polarization of the material. And that's in the upward direction. And how this behaves right at the boundary is interesting. That's pretty much the idea of refractive index, how the electric field actually behaves right at the boundary. We'll talk about that in another context. Like if this is in the z direction, at what angle should these lines come out from? That's pretty much like refraction. Whatever happens in refraction is the same principle that governs this field lines also. In fact, refraction is governed by electric field lines, which we will do in another context. And this should be compared with the slab scenario also. Slab, we had similar case where when we were doing this, this was an electric field line, and they were going in opposite directions. But when it came to D, so this was electric field lines, when it came to D, it was actually in the same direction. Slightly different quantity altogether, and the same thing happens inside the material here also. We'll do more of this next week. We'll continue on this, and let's see. Any questions?
No, I'm good.
Thanks. That's all, Matt.
Thanks.
Bye, Christian.